Hi everyone, this is Advanced Statistics for the Social Sciences. In this lecture, I'll cover proportional reduction in error for simple linear regression. Proportional reduction in error, if we recall, is calculated by using the sum of squared errors for the compact model and the augmented model. And we interpret generally proportional reduction in error as the proportion of error that's reduced as we move from the compact model to the augmented model. For simple linear regression, we are only incorporating one additional predictor into the augmented model, and so we have one additional parameter estimate in the output. So it's the proportion of error that's reduced by including this predictor in the model. Now, SPSS actually gives us information on proportional reduction in error when we conduct a simple linear regression analysis. And so we've looked previously at the table that included information on the coefficient, which related x to y. But there's also this additional table, the ANOVA table, that gives us information on model error for the overall model. You'll see that there's a row for f, a significance value, and we've talked a little bit about f before, and we'll talk about it in later slides. But we've also talked about sum of squared errors, and that information is in this table as well. It's in the sum of squares column. So to start from bottom to top in the sum of squares column, the bottom row, or the total row, is giving us the information on the sum of squared errors for the compact model. This is basically the sum of squared errors for the model with no predictor. And so this is kind of the largest error value that we work with, and they get smaller from here. The middle row, or the residual row, is the sum of squared errors for the augmented model. Okay, so the sum of squared errors for the augmented model is also known as the sum of squared residual. Sum of squares residual. And this is where we find that information. So this is basically saying this is the sum of squared errors once we have included a predictor in the model. So it's slightly reduced from the total sum of squared errors. And then the sum of squares regression, or this top row, is actually the difference between those two bottom values. So this is the difference between the sum of squared errors for the compact model and for the augmented model. And this is actually the numerator of proportional reduction in error. So when we have this difference as the numerator, and then we have the total sum of squared errors as the denominator, we have these values that we can plug in to actually calculate PRE. So I've shown you how PRE, proportional reduction in error, is calculated with these numbers. And for this smoking example, our proportional reduction in error is 0.182. Now, proportional reduction in error is also known as the R-square effect size. Now, this is only true for simple linear regression, where we are only incorporating one additional predictor into the augmented model. But when we only have one additional predictor, proportional reduction in error is calculated in the same way as the R-squared effect size. Now, an effect size is essentially a value that gives us information about the magnitude of an effect. And the way that we interpret it is that it's the proportion of the total variability that's due to the predictor variable, or the explanatory variable, when we only have one variable in simple linear regression that we're incorporating into the augmented model. And so the R squared, as I said, being calculated in the same way as proportional reduction in error, is 0.182. So the way that we would interpret R squared, or proportional reduction in error in this example, is that the number of years smoking accounts for 18.2% of the total variability or variation in smoking intensity, the outcome. Now, I've shown you the formulas for calculating the proportional reduction in error and the effect size, but SPSS also actually gives us that information in the output. So it gives us this model summary table, and it gives us this information on the R square. So I've highlighted that cell to show you where you can find it in the output. Now, R square is also really just the R, or correlation coefficient, squared. So we can calculate it using the sum of squared errors, or we can calculate it using the correlation coefficient. So you'll see in this model summary table that the correlation coefficient between x and y, which is 0.426, is right next to the R square value. So if you wanted to calculate it yourself, 0.182 really is just 0.426 squared. Now, in general, there are some guidelines for these effect sizes so that we can determine the magnitude of our effect, whether it's small, medium, or large, basically. And the guidelines are that a negligible effect is an effect that's less than 0.01%. A negligible effect essentially means we think that this effect is probably due to sampling error or bad design or something like that, and that the effect probably really is not present in the population. A small effect would be an R square ranging from 0.01 to 0.06. That's saying that 1% to 6% of the variation in the outcome is due to the predictor. A moderate effect would be 0.06 to 0.14. And a large effect would be anything greater than 0.14. So anything greater than 0.14 essentially means anything, including any predictor that accounts for 14% or more of the variation in the outcome, that's a large effect. Now let's turn to the F statistic. What does the F statistic tell us? Essentially, the F statistic in simple linear regression tells us the overall effect of the predictor on the outcome. And this is analogous to testing whether the slope of the regression line on the plot is 0, if it's a flat line at the mean. So a significant F test implies that the regression slope is not equal to 0, and so we need some description of the regression line. Essentially, we need to incorporate the predictor, x, into our model of y. Because it's influencing that regression line in some way. A non-significant F implies that the slope is truly 0 in the population, or that x does not predict y in the population. Now, let's take a look at how the F statistic is calculated. And we have this information in the ANOVA table from the SPSS output as well. You'll recall that the mean square error from the textbook and from previous lectures is the sum of squares divided by the degrees of freedom. So in this table, we get the mean square error for the regression model from the regression row and the mean square column. Now, if we look at the sum of squares, we see that the mean square error regression is the sum of squares regression divided by the degrees of freedom, which is 1. And the mean square residual is the sum of squares residual, 309.357, divided by the degrees of freedom, which is 13. Now, to get the F statistic, we divide the mean square regression by the mean square residual, and that results in the F statistic, which is 2.885. Now, essentially, the F statistic, this is an observed F statistic value that would be compared to some critical F value. And you could do this using an F table, but again, SPSS just does all of this for us. And next to the F statistic, which is sort of the overall test of whether or not our our augmented model is significantly better than our compact model, has the same p-value as the regression coefficient. So the p-value here for the F is 0.113, and that was also the p-value for the B1 coefficient. And that's because we've only incorporated a single additional predictor into the model, and so there was only one additional parameter estimate, the B1 parameter estimate. So the p-value is going to be the same for the B1 parameter estimate and for the omnibus F test. Now, let's talk about how we would report these results in APA style. There is a slightly nuanced interpretation of these results over maybe other results that we might get, because as you recall in the last video lecture, we talked about how although we saw what looked like a positive relation in the plots, the overall test was not significant, and the test of the B1 coefficient was not significant. And then in this lecture, we've looked at the proportional reduction in error and R-squared, and we saw that the proportional reduction in error actually meets the criteria for a large effect size. It was 0.182, and we know that the cutoff for large is anything greater than 0.14. So we basically need to figure out a way to incorporate all of this information into a paragraph of results for this study. So this is how we would do that. We would say we performed a simple regression analysis to assess the influence of years smoking on smoking intensity. The R-squared from the analysis revealed that years smoking explained approximately 18.2% of the variation in smoking intensity, such that one additional year of smoking increased the number of cigarettes smoked by B1 equals 0.738. Despite the large effect size, the regression F-test was non-significant, and then we would report the F, which was 2.8, and P equals 0.113, meaning that we cannot rule out sampling error as an explanation for the observed association. Now here is a place where you could also add in a sentence about the small sample size, N of 15, and indicate that you think that although it could be possible that there's a small effect in the population, our sample was not large enough to detect the small effect that we think might be present in the population. This concludes the fourth lecture on linear regression. In the next lecture, I'll explain centering predictor variables and discuss why it's useful.